So where we wound up before break, and I hope you all had a good break, and I should remind you too, we have an exam on Wednesday night, and I have a lot to cover today, and everything I'll cover today will be on that exam. So what I'm going to do is cover this outlines fairly briefly, and you'll at least get a pretty good background of where we're headed today. But where we left off last time was we talked about digestion in the bulk phase versus digestion in the unstirred layer. And that's what we're going to pick up today. We're going to talk about the idea that in the small intestine, two places where much of the digestion occurs. In the central region of the lumen of the small intestine, that's intended to be the bulk phase. And that's the region where the smooth muscle is sloshing the fluid back and forth and back and forth. The enzymes that are mostly regulating digestion in the bulk phase are the so-called pancreatic amylase. This was pancreatic amylase that had been released from the acinar cells. These are the acinar cells of the pancreas. And those enzymes now were moved into the small intestine. And in the small intestine, amylase converts polysaccharides, starch, and amylopectin into maltose. Maltose is a disaccharide. It's composed of two molecules of glucose. The other major players from the acinar cells were trypsin and chymotrypsin. Remember, they were secreted as inactive precursors of trypsinogen and chymotrypsinogen, but in the bulk phase of the small intestine, they now become active as trypsin and chymotrypsin, and their function is to convert proteins, great big long proteins, into peptides. Their function is not to generate individual amino acids, but instead to make these big proteins, these big peptides. And then we'll do the final digestion of the peptides when we're in something called the unstirred layer, right along the apical surface of the enterocytes. The third character is lipase. This is pancreatic lipase. Its function is to convert triglycerides to monoglycerides and fatty acids. But of the three, the lipase has the biggest problem, the greatest difficulties, because where amylase and trypsin and chymotrypsin are working on water-soluble molecules, proteins and polysaccharides, the lipase has to function as an aqueous enzyme working on hydrophobic molecules. And so what happens is that we have to go through this long song and dance to make more of the triglyceride surface area available to the lipase, and we'll see that's the function of bile. So in the initial description of digestion, we're going to talk about amylase and trypsin and chymotrypsin rather. And then we're going to talk about the anatomy. The anatomy here that I want you to hold on to is that the villi are multicellular structures. They're composed of hundreds of thousands of individual enterocytes. But each enterocyte has an extension of its plasma membrane called a microvillus, or taken together, the microvilli. In the microvilli, these finger-like extensions of individual enterocytes peek up into the unstirred layer. So up here, we're talking about a stirred layer. In the middle, we're talking about the region of the intestinal fluids which are being squished back and forth and back and forth. But as with all fluids in a tube, the fluid right against the wall doesn't move very much. And this is called the unstirred layer. It's 30 to 40 micrometers thick. So it's a very thin layer of fluid that we're not stirring about. And then movement of molecules in this unstirred layer is almost entirely by simple diffusion. But by the time we get molecules into the unstirred layer, from what's happened up here, we're dealing mostly with disaccharides in the form of maltose, other disaccharides in the form of sucrose, and also some in the form of lactose. The enzymes which deal with the disaccharides, maltose, sucrose, or lactose, are all transmembrane proteins. They are transmembrane proteins in the microvilli of the enterocytes. And these transmembrane proteins, maltase converts maltose into two molecules of glucose. Sucrase converts sucrose into a molecule of glucose and a molecule of fructose. Lactase converts lactose into a molecule of glucose and a molecule of galactose. But again, disaccharides converted into monosaccharides. That's all going to be done right next door to the extensions, the microvilli of individual enterocytes in a region called the unstirred layer. The pattern in the bulk phase was to convert proteins into peptides. But now most of the absorption of amino acids is going to occur as individual amino acids. So again, we see that among the transmembrane proteins, among the so-called brush border enzymes, those enzymes which are transmembrane proteins in the microvilli, will have amino and carboxypeptidases. Reminding you again that all peptides, all proteins, have a carboxy end and an amino end. And what's happening with these transmembrane proteins is they're clipping off one amino acid at a time, either from the carboxy terminus of the molecule or from the amino terminus of the molecule. So now we've rendered these gigantic proteins in steps into individual amino acids. And then there's the idea of epithelial transport. And epithelial transport is just as we saw in the proximal convoluted tubule. It's even the same genes. And what we'll see is that in the apical surfaces of the enterocytes will be transmembrane proteins as sodium-driven cotransporters. So they're going to snag an ion of sodium and simultaneously snag a glucose molecule and move it across the enterocyte plasma membrane. And then there on the basolateral surface, just again as we saw in the proximal convoluted tubule, will be transmembrane proteins. For glucose, it'll be GLUT2. It's going to now, through facilitated transport, move glucose out of the enterocyte. But those basolateral surfaces of the enterocytes are going to be strategically located so they're right next door to the endothelial cells of the hepatic portal veins, or the capillaries of the hepatic portal vein. So now we'll move the individual molecules, hexose sugars and individual amino acids, or through the cytoplasm of the enterocytes, across the basilar plasma membrane, and then into the blood vascular compartment now. But now this blood vascular compartment is the hepatic portal vein. The hepatic portal vein is going to carry these molecules to the liver. But the liver is not just one gigantic amorphous structure. The liver is broken into segments that are, a couple, 3 millimeters across, called liver lobules. And each of these liver lobules then is supplied with blood. About 30% of the blood comes from the hepatic artery, carrying oxygenated blood. But the remaining 65 to 70% of the blood is coming from the hepatic portal vein. One of the major ideas you want to hold on to when we talk about the liver and the liver lobules is the hepatocytes. The liver cells are sitting right next door to the endothelial cells of the capillaries in the liver. But the capillaries in the liver have a special name. They're called sinusoids. So these liver capillaries called sinusoids will have their endothelial cells right next door to the hepatocytes. And now we can remove the glucose and amino acids from the blood and store it in the hepatocytes. And the hepatocytes now will take glucose, convert that glucose into glycogen, which is, if you put your phone away to appreciate it, it's a lot like starch or amylopectin. So it's 1,4 and 1,6 linked glucose molecules, and we'll reconstruct those in the hepatocytes, and the amino acids will be then reconverted into protein in the hepatocytes. But the other thing the hepatocytes do, in addition to storing and polymerizing those molecules, is they make something known as bile. Now, bile that we're going to talk about today is very, very different than bilirubin and biliverdin that we talked about earlier when we talked about the blood. With bilirubin and biliverdin, those are waste products that are derived from the breakdown of the porphyrin rings of hemoglobin. But now, the bile generated by the hepatocytes has a specific role and function to do. The bile that's generated here is a combination of cholesterol and either glycine or taurine. The long and the short of that is that these molecules of bile are going to have a kind of endedness to them, in the sense that there's going to be a hydrophobic end and a hydrophilic end. And any time you see a molecule that has a hydrophilic end and a hydrophobic end, you can think detergent. And what we're going to do now is we're going to use the bile to emulsify fats. The fat that you eat in an aqueous environment of your stomach and small intestine tends to be in big globs. So what we'll do is we'll use the detergent action of the bile to emulsify the lipid. Not digest it, but emulsify it. Make it into tiny BBs of individual fat droplets, and those fat droplets now can be worked on by the pancreatic lipase. The digestion is by the lipase. The bile is simply for emulsification. We're then going to see that once the lipase is worked on these tiny droplets of fat, it's going to convert those triglycerides to a molecule of monoglyceride and 2 molecules of fatty acid. Those micelles of fatty acid and monoglyceride will now get into the unstirred layer, become adjacent to the phospholipid bilayer of the enterocyte, and move right across the phospholipid bilayer into the cytoplasm of the enterocyte. And then we start all over again. We take those monoglycerides and fatty acids and reconvert them into triglycerides. Once we've converted them into triglycerides, actually that's done in the endoplasmic reticulum. Then in the Golgi apparatus, we complex those triglycerides with protein and make something called chylomicrons. Chylomicrons are a mixture of triglycerides and protein. And those then will be secreted as chylomicrons from the enterocyte into the extracellular space. And those chylomicrons are much, much too big to get into the blood vascular compartment. They're too big to pass between the narrow gaps that exist between adjacent endothelial cells, but instead go into the lacteals. Remember, the lacteal is a capillary of the lymphatic system. So now those lipids, those chylomicrons, are going to be dumped into the lymphatics. And that's the reason why after a big meal you can end up with cloudy plasma if you spin down the blood.